Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help you with your understanding of how to set or how to calculate magnetic fluxes. So what we're looking at right here, we've got a wire here. We'll call it a long straight wire, current I upward. Now remember, the field lines around a wire are circular. You tell which way they run by right-hand rule. So just kind of imagine grabbing this wire, thumb in the direction of the current. Your fingers tell you which way the magnetic field lines go. Now, another important fact of life here, right? The field around a long straight wire is mu sub O over 2 pi I over r. So the big thing here is this over r. As we get further and further and further from the wire, the magnetic field falls off in strength. Right? That's going to be an important fact of life here for this problem. So what I'm going to do is I'm going to take this triangle and I'm going to move it over to here. And what we're going to do is calculate, or at least set up an integral for the magnetic flux through this triangle. Now, it's important to realize these magnetic field lines, they are going through this triangle basically this way. And the closer we are to the wire, the stronger the field. So inside here, they're very close together, but as we get further and further apart, field lines are getting sparser and sparser and sparser. All right. Magnetic flux. I'm going to start with this. The differential of your magnetic flux, your d phi, is B dot dA. In fact, really any vector type of flux, anytime you have a vector field in an area, that vector field dotted with a dA vector gives the flux through that field, where this V here is any type of vector field. It could be a gravitational vector field, a fluid flow velocity vector field, magnetic fields. So this expression right here gives the flux through any sort of area dA. Now, one thing you can't do is we can't just call this an area and take B times dA, because the flux varies as we move right to left. So what we're going to do, and I'm going to do this in red here, is I'm going to break this problem up into little pieces, little rectangles. Okay. The area here, I'm going to call that dA, is equal to whatever this is times, I guess what I'll call dx. So some sort of, what should I call that? I'll call it y times dx, where this red distance here is y. Now you notice that varies as we move left to right. Well, if I put a coordinate system origin right here, this is a linear function, and it's pretty easy to show that y is going to equal h over L times x, where this now I have just defined as x. All right. Now, along the surface, the magnetic fields are in the minus k direction in what I would call a standard xyz coordinate system. So if I put my dA in that same direction, the angle between them is 0. So the flux through this red area here would be equal to the magnetic field at that location. And I'm going to go ahead and just insert this. Mu sub O over 2 pi I over x, because I've now defined this distance as x, times the area of the rectangle, which is its length, given by this, h over L times x, and then times the thickness, dx. The angle between the magnetic field and the dA vectors are 0, cosine of 0 is 1. So then, right, the next step here is to integrate. So our total flux now, this would have to be integrated. And I'm just going to leave everything there. Mu sub O over 2 pi I over x, h over L times x dx. And then that integration would run from 0 to L in this problem. Now, I'm going to leave it the way it is, because my intention here was not to work this out to completion. It was just a video about how to set up an integral flow for flux. So this part of it, right, that's coming from here, magnetic field due to a long straight wire. Get some more colors to choose from here. And then this is the area of this rectangle. And of course, you know, you can see that this in this example, these x's will in fact divide out, and then all of this can be brought forward, and it ends up being a pretty simple integration. I'm not going to finish it because, again, the point of this video is just how to set up the integration. So I hope that this has helped with setting up flux integrals. Have a great day.